We now come to hypothesis testing, and you might think that you've done this before. So what sort of hypothesis testing are we doing over here? If you think about it, you come up with a regression equation where your y is equal to b naught plus b1 plus b1 times x, and then an error term. The b naught and the b1, these are estimates given to you by the regression equation. All right. You might have a view that b1 needs to be something. That might be your view. Then you will run hypothesis tests on these coefficients, either one or both of these coefficients, to determine whether the data is validating your conviction or your hypothesis. So that's where hypothesis testing comes into this context. And rather than give you a long explanation, I will give you an example that hopefully you can relate to. If you can't relate to this example, then that will question what you learned at level 1. Okay. Suppose we regress a stock's return on a stock market index's return and find that the slope coefficient is 1.5. Now, what is that slope coefficient? When we say slope coefficient, it's this. If you recall the relation y is equal to mx plus c, the m is the slope. So notice, what is m analogous to? It's the b1. So this b1 is sometimes called the slope coefficient. So this is the b1 hat. Why am I putting a hat on this? Because this is the estimate. This is what the regression software is telling you. So that is 1.5. And then the standard error is 0.2. The standard error is written like this: S B1 hat. So I'll also write it over here. S, which stands for the sample standard deviation, B1 hat. So this is the standard error. Now, just for now, take this, let's just call it the standard error. Later we'll get into the interpretation. You might also recall this from level 1. But again, just take this as a given that the regression software is telling you that for B1, the standard error is equal to 0.2. Assume that we have 62 monthly observations. So what is N? That is 62. The hypothesized value of the parameter, this parameter, we are focused right now on B1. So that will just be written as B1. No hat, because it's not an estimate, it's the hypothesized value is 1. This hypothesized value is the market average slope coefficient. If you regress the market against the market, the slope coefficient will be 1. Now, what do you think B1 is in terms of terminology that you've seen before? B1 is nothing but beta. The beta from CAPM, what is beta? It shows the sensitivity of a stock's return to the market return. So if you are regressing Y, which is the return on a given stock, with X, which is the return on the market, and you get a certain line, the beta is nothing but the slope of this line. And that is nothing but B1 from our regression model. Okay, so the null hypothesis is 1, and you are seeing whether this value of 1.5 is statistically different from 1 or not. So we will run a hypothesis test. How do we do hypothesis testing? What's step number 1? The first thing that you do is define the hypothesis. Alright, so what is a null hypothesis? Let's set up a null hypothesis that B1 is equal to 1 versus an alternate hypothesis that B1 is not equal to 1. So this is step number 1. Then we compute the test statistic, and then finally we will compare the test statistic with the critical value. How do you compute the test statistic here? There is always a formula for coming up with the test statistic. The formula here is the same basic formula that you learnt at level 1. That formula for the test statistic is equal to the value that you get from your little experiment or your data set which is 1.5, minus the hypothesized value. What is our hypothesized value in this context? It is 1, divided by the standard error. What is standard error? 0.2. I hope you remember this, but if not, again, the test stat in this context is the value that you come up with from your data, which is given as 1.5, minus the hypothesized value divided by the standard error. I think if you connect this with what you studied at level 1, there you would say you would come up with a x bar or something minus the mu naught, which was your hypothesized value, divided by the standard error. Okay, this standard error was s over root n, but I won't go into that right now since the standard error is given. There'll be more on this in the next reading. So this is our t-stat. What is the value of our t-stat then? So our test statistic is 2.5. What do we compare this with? With the critical value. The critical value, we read off the t-table, that is at a 5% significance level, the critical value is 2. Okay, so what do we do with the null hypothesis? Since 2.5 is greater than 2, you reject the null hypothesis. Rejecting the null hypothesis in this context is saying that we have statistical evidence, so to speak, that the return on this stock is different from 1. The beta is different from 1. Okay, so that is the basics of hypothesis testing over here. Very often you are given a p-value. Strictly speaking, this is something that you studied at level 1, but I know lots of level 1 candidates who pass without fully understanding the p-value. I will read the curriculum excerpt that I think is relevant, and then I'll just give you a very simple explanation. The p-value is the smallest level of significance at which the null hypothesis can be rejected. It allows the reader being you, the analyst who is looking at the result, to interpret the results rather than be told that a certain hypothesis has been rejected or accepted. So you don't want your quant guy to tell you to accept or reject. Ideally, you want to get the data. That's why you are studying this, and you want to interpret yourself. In most regression software packages, the p-values printed for regression coefficients apply to a test of null hypothesis that the true parameter is equal to 0. So what this is saying is if you are just given the p-value, obviously that is based on some null hypothesis. The default null hypothesis is that the value is 0. Now if that is not your hypothesis, then you need to come up with your own. Okay, versus the alternate that the parameter is not equal to 0, given the estimated coefficient and the standard error for that coefficient. Now I'll just put this in slightly different terms. The t-stat and the p-value are related. When your t-stat is high, what is that saying? So when you do your analysis, remember that there are certain critical values at a 0.5 level of significance. When you do a two-tailed test, what are your critical values? They are roughly speaking -2 and +2. Then you get your data, and based on your data you get the test stat. If your test stat is very high, all right, let's say your test stat gives you a number of 3. The p-value is this probability over here. Okay, so notice that a high t-stat is a good thing, because high t-stat means that you can reject the null, which is what you want to do. High t-stat will automatically mean a lower p-value. So if you are given a p-value of 0.001, will you be happy? You'll be happy, because a low p-value is a good thing. It means automatically that you have a high test stat. So with the p-value, you can then determine what level of significance you are interested in. Okay, so that is the high-level explanation. The best way to really understand this is by doing questions. Okay, let us move on. Estimating beta for General Motors stock. Now this is something that I will want you to read, but we set up a regression model where there is an alpha. What do you think the alpha is over here? This is the B naught. What is the beta? This is the B1. When you run the regression, the B1 that you get will really be the B1 hat. Now this actually does what we have talked about. So when you read this example, it should make sense given the discussion we've just had. When we run the regression, here are the regression statistics. And on the exam, obviously you will not do the regression, you will be given the regression results. So what does this multiple R mean? Actually, the R squared is this number, 0.3079. So what does R squared mean? This is also the coefficient of determination. So this is the fraction of the total variation that is explained by your model. If I just tell you to look at this data and tell me the correlation between the two returns, what's that correlation? Under root of 0.3079. And when you do this, you will notice that this is actually this number. The multiple R in a one variable analysis is actually the correlation. So that is another term for correlation. Okay, and at least once or twice in your life, do that under root calculation and see that this is the answer. Okay, standard error of the estimate that is given. Okay, but notice that this is the SEE. This standard error over here is different from these standard errors. And why am I emphasizing this? What is the alpha? This is your B0. So the regression is telling you that this is the coefficient. This is B0. And what is this?
B1.
This is B1. So if you were to write out the regression equation, what would that be? It would be y is equal to 0.00036 plus 1.1958 into what? Into, this is the coefficient, into this much into x plus a error term. So this is a x, not a multiply, right? So the question now is, the regression software, or the point here is the regression software is actually also doing a hypothesis test on these numbers. So it is telling you that for this particular coefficient, the standard error is this, and it is calculating the t-stat. It is doing the same thing over here. It is telling you that the standard error is this, and it is calculating the t-stat. So notice something. There is actually a relationship between these numbers. The regression software is giving us the standard error and the t-stat. Remember, with the t-stat, the value was equal to what you are getting, which in this case is the estimate, 0.0036 minus the hypothesized value, which the software assumes is 0. Remember, the software doesn't have any extra brains other than what has already been programmed. So it doesn't know what the appropriate hypothesized value is. It will just assume 0. Now you can have some other hypothesized value and base your test on your hypothesized value, but the software is just taking 0 divided by what?
10127.
The standard error, which is this number. This is the standard error associated with B0, which is also called alpha in this context. So you divide by 0.0127. So when you do 0.036 divided by 0.0127, what will you get?
0.28.
You will get this number. What about, how can you get 5? Same logic. Now you will do 1.1958 divided by, so 1.1958 minus 0, again that's the hypothesized value, divided by this, and that will give you the t-stat. So what is this t-stat telling you? Is it a big number? This is saying that you can clearly reject the null hypothesis that B1 is 0. You can reject this null hypothesis. So you are rejecting the null that beta is equal to 0. So what you are saying is that based on the evidence, clearly there seems to be a relationship between market returns and the returns of the stock. Okay, that is the point. Now, what if your belief is that the beta is different from 1? Then how will you change your working over here?
Minus the hypothesis value.
Yeah, then your hypothesized value becomes 1 and you will get a different T-stat. Okay, so keep that in mind. Alright, then this is important. So you will notice constantly the same sort of format. So there will be a multiple R, which is the same thing as coefficient of determination. No, I'm sorry. The R squared is the coefficient of determination. The multiple R in this context is the correlation. You will be given the SEE. This is the overall SEE for the regression. Then you will be given information related to the specific components. Obviously, depending on what you are looking at, they might give different names. So, but this first one will always be the B0 and this one will be the B1. Here you are talking about a difference, so it is a spread. When you have time, read through this. I'll just describe it at a very high level because I think from a financial perspective this is interesting. You might remember from level 1 the concept of enterprise value, that is the overall value of an entity. So high enterprise value relative to the invested amount is a good thing. So a researcher believes that there is a relationship between enterprise value over invested capital and the difference between return on invested capital versus weighted average cost of capital. This is called the spread over here. Is it good that the return on invested capital is much more than WACC? Yeah, so somebody believes that if that spread is high, then enterprise value will be high relative to the invested amount. So that's the economic theory. And then you can actually look at companies, collect data and see whether the data validates that hypothesis. So underlying that's what's happening. In the quant context, you don't really need to know all this. But as I keep saying, these examples actually highlight very useful things which connect with other material that you do. And if you do enough of these examples, then what you see on the exam hopefully will be somewhat familiar. All right, then this notice is, this is something again you need to do. Same logic, same format, lots of good practice. So if you don't have much time, you don't have to go reading the curriculum, but if you do all these examples and then you do the questions at the back, you're in good shape. All right, now we come to section 3.6, which is ANOVA. What does ANOVA stand for? Analysis of variation, and this is the most likely question you will get related to quant, because ANOVA shows up in this reading, it shows up in the next reading, and it shows up in the third reading, which is time series. And what I'll do is give you some basic information first that you need to try and remember, and then we'll do some questions. What is ANOVA? Analysis of variation, or ANOVA, is a statistical procedure for dividing the total variability of a variable into components that can be attributed to different sources. Okay, so another way of putting it is that you have some variability. Where is that variability coming from? What are the sources of that variability? We use ANOVA to determine the usefulness of the independent variable or variables in explaining variation in the dependent variable. This is another way of saying the same thing. Okay, so hopefully that was easy to remember. Can you remember this based on the name? Analysis of variation. What does analysis mean? It means where is that variation coming from? All right. An important test you do in this context where you are analyzing variation is called the F-test. And for the F-test, you use the F statistic. At level 1, somewhere at the end of the hypothesis testing reading, there was this discussion on F-test. Most people did not understand that and still passed, which is okay. If you recall from level 1, F-test had something to do with the ratio of two variances. Okay, just keep that at the back of your mind. Here you need to remember this statement. What does the F-test do? The F-statistic tests whether all the slope coefficients in a linear regression are equal to 0. So, if the F-test is significant, that means that the coefficients are not 0. I underlined all and emphasized all for a reason. This is one test which is not just looking at one coefficient at a time, it is looking at all coefficients collectively. And you are trying to determine whether the coefficients are equal to 0 or not. As an analyst, what do you want? Do you want the coefficients to be 0 or do you want the coefficients not to be 0? You will want them not to be 0, because if they are 0, then you are not saying anything. Alright. In a regression with one independent variable, this is simply a test of this null hypothesis. If you have just one independent variable, then you just have a B1. In the next reading, we'll have more independent variables, so this will be more significant. Okay, more on the F statistic. The F statistic measures how well the regression equation explains the variation in the dependent variable. Alright, so that's important. Now here is where things get the most tricky, so you will have to bear with me and just patiently listen to these things and then go back, review it several times and try to memorize. But what I've tried to do is take the most important points from the curriculum. So what is the F statistic? It is the average of regression sum of squares, which is RSS, divided by the average sum of squared errors, which is SSE. And this is something that seems similar to SEE but is different. Okay, so what I want you to do here is initially be like a kid who just uses the phone without knowing how the phone works. In fact, even we do that, right? So sometimes we use stuff without understanding it. So let us first learn how to use it, and slowly, while we will not become experts at this, but we'll learn enough to be able to answer questions. Okay, so have you remembered this fact? Okay, then the next question is, what are these guys? What is RSS and what is the SSE? The average regression sum of squares, or RSS, is the amount of variation in Y which is explained by the regression equation. Now this goes back to something we talked about earlier. If you have your Y and you have your X, there is a certain Y bar, which is the average Y. And then let's take this data point over here. For a given value of X, what does the regression equation explain? It explains this much variation, right? So this is the average. The regression equation explains this much variation. Okay, so RSS is the amount of variation in Y. This is the total variation. This is the amount that is explained by this part is explained by the regression equation. So ideally you want a high RSS. How do you compute that number? How do you compute the average RSS? It is computed by dividing something called the regression sum of squares, and these things will be given to you in the question. The regression sum of squares will be given to you. How do you come up with the average? You take the regression sum of squares and divide by the number of slope parameters. What do we mean by the number of slope parameters? Number of slope coefficients. So when you have B0 plus B1x, how many slope coefficients do we have? Only B1 is a slope coefficient. B0 is like an intercept. In this case, there is only one slope coefficient. If you have, as we will in the next reading, plus B2 times some other x variable, then you'll have two slope coefficients. But in this scenario, our life is simple. We just have one slope coefficient. So the regression sum of squares and the average regression sum of squares is the same number. Okay, so remember that. What's the next question? What is SSE? the average sum of squared errors, SSE, is the sum of squared residuals. So you take all the squared residuals, add them up. How do you compute it? It's computed by dividing the sum of the squared errors or the squared residuals by the number of observations n minus the total number of parameters estimated. So if you only have x and y, that is 2. Okay. So this is another way of putting the formula. What is F stat? It is equal to RSS divided by 1 divided by SSE divided by n minus 2. This is just putting in a formula for what we have talked about. Regression sum of squares divided by 1 gives you the average regression sum of squares, and then SSE, what does this indicate? The sum of the squared residuals, and what do you divide by? N minus 2. Now I want you to pause this over here and actually read this 2-3 times and absorb these terms. They seem to be a lot, but if you can remember this over here, it will help you with your questions later. Many students get confused between SSE and SEE, which we studied earlier. So for your benefit, I am reproducing a simplistic version of SEE, which we talked about earlier, the standard error of the estimate. Notice that with standard error of the estimate, we sum the square of the error terms, divide by n minus 2, which looks a lot like what we do over here. But with SEE, we take a square root. So we are then in normal numbers, not in squared numbers. Whereas SSE is a squared number. That is the major difference between SEE and SSE. Alright, then we come to example 17, and here you are looking at a very simple ANOVA table. So what are you looking at here? There is the multiple R, there is the R squared. You are looking at the standard error of the estimate or the SEE. The number of observations is 60. I'm skipping the text, that is something you can read. I just want you to be comfortable with this sort of a table, because as I keep saying, something like this is very likely to show up on the exam. In fact, a more complicated version of this. So here is the ANOVA table. What are you seeing over here? There is the regression and the residual. So with the regression, the degrees of freedom is 1 because we have one independent variable, one slope coefficient. The sum of squares, this is the regression sum of squares, that is given. So you will not be calculating these numbers, they will be given to you. What about the mean or the average regression sum of squares? How do we come up with this number? It is 0.1093 divided by the number of independent variables, which is 1. So that is the same number. In the next chapter, where we have more than one independent variables, then these two numbers will not be the same. They'll be linked, but they'll not be the same. Okay. Then what about the residual? This is the SSE term. This is the sum of squares, or this is the first number, 0.0176. How do we go from here to here? You divide by n minus 2. What is n? N is 60. So 0.0176 divided by 58 and you get this number. Okay, so how do you come up with the F stat then? Where does this 359.6 come from? You divide the 0.1093 divided by this little number and you get a very high F stat. Is this good news? This is good news. This is telling you that your regression is quite useful in predicting the value of the dependent variable. Okay, and then what do you have over here at the bottom? The coefficients. So this coefficient is it's almost 0. the slope coefficient or the beta is 0.7 and the standard error is this. What is the t-stat? The t-stat is a big number. So what is this telling us? This is telling us that based on the data, this number is significantly different from 1 or from 0? From 0, because the software just assumes 0. You can run a hypothesis test with 1, okay, in which case you will get a t-stat and then you can determine whether the result is statistically significant or not. Okay, we are coming close to the end. There is 3.7 and then there is one little section after this. The prediction intervals. We use regression results to make predictions about a dependent variable. So ultimately this is what we are after, and in any question that you will get, ultimately this is what will happen. You will be given y is equal to, so you will come up with a b0 plus b1 x plus e. In this case we just have 1x, in other cases we'll have maybe more than 1x. You will be given b0, b1. What is the benefit of having this equation? The benefit is that if you have a linear regression like this is your regression model. For a given value of x, you can now predict y. Let's say that the data does not give you a value of y, but based on your model, you can predict the value of y. So the question now is, when you predict the value of y using your model, how much confidence do you have in that prediction? Is that an important question to ask? It is. So that is what we are talking about. Then the concept of prediction interval means that if you are predicting y, is that an exact answer or that's your estimate? That's an estimate. So if you predict a number of say 90, whatever, based on whatever you are doing, this is an estimate. If your boss asks you what is the value of y, whatever the y might be, most probably you will give a range, right? Around 90. So that is what this section is about. How do you come up with that range? Okay, now let's go into the details of what I have said over here. Again, all this is from the curriculum. We use regression results to make predictions about a dependent variable, obvious. It is important to understand how to compute the confidence intervals around the regression forecast. So you're forecasting something and then you need to be able to tell your boss that with 95% confidence, the actual number is somewhere in this range. And that range will be around 90 plus or minus something, 90 being the number that you are predicting using your model. Now, there is uncertainty involved. What are the sources of uncertainty? One is there is an error term. Will there be an error term every time? Yeah, there will be some error term. You don't know what that error term is. The expected value is 0, but the actual value will be plus or minus, it will be something. So does that introduce uncertainty? Yes. There is also uncertainty in the estimated parameters. The b0 and the b1 that you estimate, are you sure they are 100% accurate? No. So there is uncertainty there. So between the uncertainty associated with the coefficients and the uncertainty associated with the error term, there is overall uncertainty. Okay, so from an exam perspective, know that these are the two sources of uncertainty. Okay, now there will be a certain prediction error, which is the difference between the predicted value and the actual real value. You don't know that actual real value, but it is out there, right? What you need to be able to do is estimate the variance of the prediction error. Again, prediction error is the difference between your estimate and what the real value actually is. Now, I don't think you need to memorize this formula. If you want to be super diligent and you are good at memorizing formulas, do this. I'll confess, I never learned this formula and it didn't really hurt me. Okay, but there will be 1 or 2 questions in the curriculum at the end of this reading which ask you to use this formula. My advice is just use it once and you can see, based on the variables over here, you can see what this error depends on. Just if n is high, what happens to the prediction error? It comes down. Does it take a rocket scientist to figure that out? No, it's intuitive, plus it is apparent from here. And you can also see the other relationships from this formula. if the formula is given to you and the various numbers are given, you can plug and come up with this. The more important thing is to understand this interpretation. Do you want a high number here or a low number? You obviously want a low number. If you have a low number, then your confidence is more. Let's say that this number is given to you in a particular question. You are given the variance of the prediction error. And then you are asked to come up with a confidence interval. And this connects with level 1 again. How do you come up with confidence intervals? You take your estimated value, and where does this come from? From the model. And how do you think we symbolically represent this? Y hat. Whenever there is an estimate, it's a hat. And then the range around this will be plus or minus your critical value times the SF. So if SF, let's say just pick a number 0.5. I don't know if you remember this expression from level 1, but your confidence interval is the predicted value plus or minus your critical value times the standard error. This is sort of the standard. You take the square root of the S squared, which would be given to you, and plug that over here. And what is this number? This is based on your confidence level. If your confidence level is 95%, what is the significance level? 0.05. And then you look up your T table based on N and you come up with your critical value of 2. If you want to give your boss an answer with 99% confidence, what will happen to this number? Go up or go down? It will go up. Alright, and if you are having trouble over here, then you go back and refresh your memory on level 1 hypothesis testing, and these videos on hypothesis testing are available for free on our website in case you are rusty on this material. So this will allow you to come up with a confidence interval for your prediction. Alright, and then I want you to work through example 18, where given these numbers you can actually come up with the prediction interval. Actually, the numbers are all given. You just need to plug into the formulas and come up with your answer. Alright, last point. Regression analysis is important. It is extremely useful, but like any other tool, there are limitations. And the CFA Institute wants you to understand those limitations. When you do an analysis, it's for some data which has been taken for some time or some set of companies. So it's either cross-sectional data or time series data, but it is limited. Relationships change over time. By definition, any analysis that you do is limited to the information that you have. Okay, so if you're doing a time series analysis for the last 10 years, maybe the next 10 years scenario will be different. Sometimes it is difficult to apply. There are specification issues. This becomes more significant at the next level. But how do you figure out what's the dependent variable? What is the independent variable? What are the appropriate independent variables to use? Sometimes you might want to do a transformation where you know that the relationship between y and x is of the form y is equal to x squared. Then your independent variable needs to be a transformed version of x. Sometimes you need to use logs and exponents and so on. So setting that up is partly an art, partly a science. Fortunately for us, we don't need to do this because it will be given to us. In the real world, you really need to understand the economics of your environment in order to properly set up the regression equation. We very nicely defined some assumptions. Sometimes those assumptions are violated, so we need to then use some techniques to address those issues. Usefulness is limited for investment applications since all participants can observe relationships. This is making a larger point that if you think you're really smart, you can do a regression, make predictions, and then make superior investments based on those predictions. It will be silly to think that others can't do the same. If there is something glaringly obvious based on the data, chances are that other people who are smarter than you have already figured that out. Right? So keep that in mind. All right, we are done with the first reading in quant. I'll give you a quick summary. We first talked about correlation analysis. I'll skip the details because most of what you saw here is an overlap with level 1. Correlation is a measure of the relationship between two variables, ranges between -1 and 1, 1 being perfect positive correlation, -1 being perfect negative correlation. Here is the formula that we need to remember, because when you do a correlation analysis, you'll be picking some data and there'll be a correlation of say 0.8. Is that statistically significant? We don't know. It depends on the hypothesis test. To do the hypothesis test, you come up with a hypothesis. The hypothesis might be that the population correlation is 0. And then you come up with a test stat which takes R. This is the correlation for the sample, multiplied by square root of n minus 2. N is your data size, divided by 1 minus R squared. This is your test stat. What will you compare this with? The critical value, which will depend on the size of the data set. And then you compute the degrees of freedom, which will be n minus 2. And then you decide whether the number is statistically significant or not. You are more likely to see something on linear regression. Okay, so here remember the assumptions. Understand the basic idea behind linear regression, that you are creating this line, dependent variable, independent variable, y is equal to b0 plus b1 into x plus an error term. We talked about SEE. So here we took the residuals, added them up, actually squared them, added them, divided by n minus 2, and then took the square root. Okay, what is R squared? Also called the coefficient of determination. This is a measure of how well the data is explained, and it becomes more precise. There are formulas associated with R squared. It's the explained variation divided by the total variation. Then we do hypothesis testing. The hypothesis testing is for the B0 and the B1. Remember all the things related to the F-stat. So the key points I told you. What is F-stat? So the formula for the F-stat, the RSS divided by 1, all of that divided by the SSE divided by n minus 2. So remember those. What is the interpretation? Is high F-stat good? Yes. That tells you that your regression is meaningful. And then finally we just talked about prediction intervals. This, by the way, is the formula for the F-stat. All right, now your job is to read the summary also in the curriculum. What I have found very useful is the curriculum summaries. They take all the points. Even these summaries span sometimes 2-3 pages, but that is much better than reading 40 pages. Okay, you can read the 40 pages, but the summaries are generally good. Learning objectives. I'll make a comment on these over here. A lot of people don't focus too much on the learning objectives, and some study notes just base everything on learning objectives. But I think sometimes that compromises the flow. In my view, here is how you use the learning objectives. The learning objectives in the curriculum are stated right in the beginning. Once you are done with the reading, then go back and see whether you can actually answer those learning objectives. The learning objectives are stated as questions. So they say, define RSS or define this or interpret that. So see whether you can actually do what the learning objective is asking you to after having gone through this lecture. Examples I've emphasized before, and I'll emphasize again that do them. If they seem long-winded, then at least read them. As you spend more time on this material, it will become obvious which examples to spend more time on. The practice problems at the end are important, especially the case studies. In this particular reading, there'll also be questions which are not case study based. They just calculate the covariance, calculate the correlation, calculate the standard error. So it's like straight out of a textbook. Now, if you have time, then do that. If you don't have too much time, then read the solution. And then try to also do practice questions from various other sources.